So good afternoon, everybody. I'm Emmanuel from Atos, a French company that operates worldwide in the IT and service domains. I'm working with Jez Wayne, who did this work on neural networks, machine learning, and artificial intelligence on power platforms and the OpenPOWER AC922. So all the credits go to Jez. And one of the projects we are working on is with the European Space Agency. Click, click. It doesn't move. Okay, thank you. So one of the projects is named Gaia. In 2013, the European Space Agency launched into space that satellite Gaia on top of a rocket, a Soyuz rocket. And so they positioned that satellite on the second Lagrange position. It's 1.5 million kilometers away from Earth, and this is where the centripetal force counterbalances the Earth-Moon gravity. That second Lagrange point has also an advantage, is that the satellite is not in the direct sunlight, it's in the shade. So it's better to map the Milky Way and take pictures. So the satellite, it's made of, there is a camera on that satellite that is a 900 million pixel, so very, very fine camera, and it takes a picture of 2 million stars every hour, so it's roughly 50 gigabytes of data per day. And the angular accuracy of that camera is measured in micro arc seconds. And just to give you an idea, the precision of that camera is 10 micro arc seconds. So it means that if you are on Earth, with that camera, you are able to distinguish two nickels on the Moon. This is the precision of the camera. And on that camera, there are two mirrors that are 60 degrees apart, and the satellite rotates and is sweeping across the sky permanently. So the goal of the project is to bring the most accurate map of the Milky Way to date. And so far, we know that there are 200 billion stars in the Milky Way, and some asteroids bodies and some asteroids in the solar system. And all the data that we have up to now on the Milky Way is this collection of books. It goes way back to 1996, where during the Hipparcos mission, they took pictures and cataloged some stars, and with the Hipparcos mission, we have a good accuracy of the star of 100,000 stars, and a less accuracy for about 2 million. So this is a huge, huge step, going to 2 million stars to 1.7 billion. So a big move forward. So the data was issued by the ESA in April 2013. And this is at the time that they announced there was 1.7 billion stars. So the accuracy is about 200 million, and it represents only one book. And so we have almost 100 books to write. So big work to do. Ooh. Mm-hmm. Okay, so let's go back. Okay, so this is what you see here on screen is a picture of a synthetic map, because what we take is not real picture with the camera, but this is only measures of the brightness of the stars and things like that. So this is what we got. And on the bottom right here, you see these two bubbles are the Magellan clouds. They are the our two neighbors galaxies that are far away and bigger than ours. But this is what we see. So if you ask yourself where we are, the sun is there. We are here in that map. So the team we are working with in the European Space Agency is based in Geneva, in Switzerland, and they are specialized in the variable stars. And these variable stars are important because we measure the intergalactic distances based on the mass and the brightness of these variable stars. And a standard candle is a class of astronomical objects that belongs to the same class and have a standard luminosity or brightness. And you can actually determine the object distance from the Earth on their own feature. So it means that, for instance, in the variable stars, we have also two types of class. We have intrinsic variable stars. So it means that that star is changing based on its own feature. It means that the star grows with a certain period, and for instance, the Cepheid stars, they grow in between 1 and 70 days. And we use them as the reference to do measurements. So this is a very good reference point. And once we have determined the specific Cepheid luminosity and variability, then we are able to determine the distance. So they have also different, let's say, features. They can be pulsative, they can be eruptive, but we have also another type of variable stars that are extrinsic. And these stars vary, but on external conditions. For instance, if there is a dust cloud, the luminosity of the star will go down, or if a star is passing in front of the other, then you will see the brightness of the star that will decline. And this is that type of graph that we can see with the variation of magnitude or luminosity. So we try to classify these data, these stars, into that tree. So the variable star, there is the same classification for the non-variable star, but here we consider only the variable ones. And among these stars, you have, oops, let me go back. You have, for instance, I messed up back. Here you have the classification, the pulsating, secular, cataclysmic, and the whole project, the whole point of the project is to try to classify these 1.7 billion stars, to fit them here. We may, maybe at some time, discover a new type of star or whatever. With the traditional approach, we use the logistic regression, the k-means or the random forest or the support vector machines. But here what we are trying to achieve is to use the machine learning algorithm to classify these stars. So the data that we got. For each star, we get 150 attributes per star. So the color, the speed, if it moves toward us, away from us. Also some compound attributes, such as the red minus blue value. And this is very important because in the spectral measure, the red indicates when the stars move away from us, and the blue when it comes toward us. So this is a significant piece of information. And some other details, the number of observation of the stars. This is not so meaningful, but we have that in our data set, the ID. And we have also a bunch of statistics on statistics. The means, the skewness, the kurtosis, the tail of the shape, signal to noise, many statistics. And so we'll have to classify all these info. So the data, what it looks like, it's a big Excel table, 150 columns and 100,000 of rows. So we have here in that example, we have the photometric value, the blue photometric minus the red photometric, the blue photometric with the brightness, the mean brightness, and so on. All the data that you have here are not the real data, because the real data are under a non-disclosure agreement with the ESA. So, but it looks like that. So what we tried to do, we got the data set. At first, can we do something with the data set? Well, we tried first to plot the information. And guess what? Here we see two red bubbles. What they are? They are the Magellan clouds. So the data set is quite healthy because we are able to define some star, or Lyrae, the Cephids, the Mira, or whatever. We have something meaningful in the data set. So what can we do with that? We can go further, and the whole point of the machine learning and the algorithm, the neural networks that we will try to set up is to classify these stars. So just draw a line and say, okay, below the line, this is that type, above the line, this is another type, and so on. And so we tried to plot different graphs, and this is what we got. So traditionally, this is done with the statistical techniques, the k-means, but again, our point was to try the machine learning algorithm and see what we could get out of that data set. So we did some cleanup before processing the data. Well, we removed what was, in our sense, not so meaningful. The number of observation is useless to classify the stars. Unfortunately, some rows were with empty value, so we had to remove this value. Some values were not numerical, so we had to put them in numeric. But the most important thing is that we normalized the values. Because in the data set, we have big numbers, small numbers, and the machine learning algorithms are not very efficient at dealing with big numbers. But this is a regular operation that we do. We normalize, and we put the data between -1 and 1 or 0 and 1. So we did the normalization on the data. So will it work? So just to give you a quick recap on the neural network, this is what you have up here. We have in input a data set. We have a neural network. We feed the neural network with the data set. And the neural network will adjust itself, tuning, diminishing the output errors and looping at that. When the model is quite efficient, then we get the actual model that we will use, and in our data set, in our model, we will train it, we will inject a new data set to that model, and we will see what is the prediction of the model, what is the classification of the model. So this is the way how the machine learning works. So the approach that we took was to load the data into the CSV file, delete what was, I would say, useless or redundant, normalize the value, split the data set in two, because it's important to train your model with, let's say, 80% of your data set. You save 20%. When your model is well trained with a good accuracy, you need to test it. So with the remaining 20%, you test your data set. As you know what you put in input, you can determine if the prediction of the model is good or not. So we did that, and to achieve this, we use some frameworks. And here we use the frameworks that IBM made available. That is the Watson machine learning framework. It's a fully packaged and tested software suite. It installs very easily, no pain. You bring it up in, let's say, a few minutes. It's a matter of installation time, so very quick. And it's a real pleasure to work with it, because everything is there, is tested. You don't need to get any missing dependencies or whatever. You have the full set working in a snap. So we use the pandas, and the pandas is a Python library to manipulate the data structure from raw data into some different format. We use the NumPy library, that is the numerical Python. This is an important fundamental package for the scientific computing. It brings a large collection of high-level mathematical functions. We use Keras. Keras offers a higher level and more intuitive set of abstraction to TensorFlow, and it's easier to develop with Keras. And we use scikit-learn as well, because it provides a range of supervised and unsupervised learning algorithm with a consistent Python interface. And all this run on the OpenPOWER AC922. So just a quick look at the code, and the code is really, really small. Here we load the data into the Panda frameworks arrays. We remove the not meaningful rows and columns. Then we split the data set in two, 80-20, 80 for the training, 20 for the test. We normalize the value, and then and then we are ready to go. We are ready to train the network. So we build the Keras model. The model is sequential. We add in these two lines, we add the hidden layers of the model. So the first line is an input layer and a hidden layer. The second line is the second hidden layer, and the third line is the output layer of the model. Then finally we compile the model. Come on. Okay, so this is the model that we get. In the input, we have our 150 attributes, so 150 neurons, 2 hidden layers, and output or classes or star classes. This is the model that we have at the end. So now that we have the model, we are going to train it. And to train the model, we define some parameters, the number of epochs, the batch size. So many what we call usually hyper parameters. And then we assess how we did perform, how the model did perform. So this is what we get. First run, we got 87% accuracy in star classification. This is really impressive. So the accuracy is just the sum of the true positive and true negative divided by the whole predictions. And this is look very promising because this result is close to what we get with the traditional method and the logistic regressions. So the refinement, we can do some refinement to try to get a better accuracy. And one thing that we have to fight against is the overfitting of the model. So the overfitting is, here we have some data points and we try to classify these data points. And we say, okay, above the line, this is one type of star, and underneath, this is another type of stars. This is the way how the classification works usually. But if we leave the model trained, let's say, too long, then we end up with a different line, where the line goes through all the data points. This is what we get. So here the model is very, very good, performing very well, 100% during the training phase. The drawback of this overfitting is that when you inject your test training, it starts diverging and you do not have the 100% accuracy. So there is a way to, let's say, manage that. And one way is to put a layer in the middle that throws away 20% of the result. This is the one way. There are other techniques to do that, but this is what we did, and this prevents the overfitting. So the hyperparameters of the model, we choose the geometry, the number of layers, how wide it is, but then we have some other parameters to set. For instance, the activation function that at the end of each neuron of the network, it limits the output of that neuron between 0 or 1 or minus 1 and 1. We can use the rectify logic unit, but there are plenty of activation functions. So we have to test not all of them, but many of them. The learning rate is that the step that we take toward the best result or the optimum. So if we take a large value, we will go fast, but we can skip over that minimum. If the learning rate is too narrow or too small, then we will spend time running to reach that minimum or that optimum value. We have also metrics, how the model performs. We have the batch size. Should we feed 1 star, 10 star, 100, the whole set? We have to determine that. Which technique do we use for the overfitting? So we have here 7 parameters to adjust. If we put 10 values on each of these parameters, we end up with 10 million combinations. And so if we have to test this 10 million combination, it's better not to start. So the approach that we took is that we used the scikit-learn, and in the scikit-learn we use two functions. The random search, so what it's going to do is to pick up parameters randomly, and by the end we will get about two good models, and around these two good values or models we will use the grid search to refine the accuracy of the model. We've wrapped that into Keras, the Keras model to make it usable by scikit, and this is quite easy to do because it's a dictionary. So you put the parameter name, you put the list of value, and then scikit-learn do the job. So the optimization behind that. As I said, we have a lot of parameters, many attributes, so the training time is very, very long. This is where the OpenPOWER AC 922 comes into play. Because from the architecture point of view of that server, you know there is the NVLink bus between the GPUs and the CPU, and this is really, really a fast machine. And we got that server, and that was very, very impressive how it is fast. So here we have a lot of statistics about many variables. So we have to optimize these statistics, and the scikit toolset allows to identify the columns that are correlated between these parameters, and anything that is correlated above 95%, we keep just one column. So if we have, let's say, 5 columns correlated, we just keep one. And this is important because doing so, we are shrinking the number of attributes, and so we will take less time to train the model. So the optimization that we used, we removed the correlated features or columns. We used pandas to measure that correlation, and above 95%, take it away. We tried also a different technique, that is the primary component analysis that is provided by scikit-learn as well, and you have here just a few pieces of line to test that. It's based on the variance of the attributes, so it reduces the number of features, and it retains only the variance between the column. And we will see in the result where we stand with that techniques. So with this refinement, we end up with that accuracy, 94%. We went up from 87 to 95. And so here is what we know about the values, and here is the prediction. So for instance, for the RR Leary, the model is quite good because the prediction is 96% for that class of stars. Here you can see that there is some area for improvement. So here is the comparison, and what we did, we took first the full data set, and we got an accuracy of 93%, and that was our time reference point. And if we remove the correlated functions, then the accuracy is about 94%, it's better, but we see that we save 20% in time. And if we use the PCA, then with the PCA, we divide the time by 2, but we are losing the accuracy. So this is the reason why we dropped off the the PCA method. So the future work on this project with the ESA, the next step could be that the satellite collects more data, and we have some data to explore around the color measurement. From red to blue, the measurement over time, because here what we did, it was the data set and let's say a picture at one point in time. But we have a lot of data because the stars are moving, so we have the same data, let's say, the next point in time and so on. And so we have to process this information that was not part of our first attempt. The other experiment that we could use is the recurrent neural network. That technique is in your cell phone. When you are texting, it uses what you typed previously to predict the next word and propose the word. So this is the principle of the recurrent network, and we may try to use that technique to see where we can go with that. Yes, one point as well, how can we deal with the missing data? Oops. So the lessons learned. As I said, the OpenPOWER 922 is really a good machine, very fast. The training is about a couple of minutes. If you run that, let's say on your laptop, it's a matter of hours, even days. So we use the Watson machine learning accelerator. As I said, easy to use. This is a tarball, you explode it, it's all installed, everything is there. You just have to kick the tires and it's okay. What we would like to explore is the distributed deep learning. So far, we could train the model over the 4 GPUs of the AC922, and we have not tried that yet, but we would like to give it a try. Working with Keras, that's quite easy. You've seen the code, not all lines were there, but it's about 50 lines of codes to achieve this. And then at the beginning, we didn't know if with the neural networks we were able to, at the end, achieve something. And what we did, we got good results. And so that's something, it's a topic that we have to carry on with. And then, so if you have any questions, not about that picture, because the only thing that I can tell you is where we are, but that's it.
Are we there or a little bit to the right?
We're on the left. Just
on the left, okay.
So thank you.
Anybody have questions? Oh, yes, great, excellent.
Yeah, what would be the main advantage of using a machine learning process to do that instead of a classical procedural type of work?
Two things. With the classical statistical method, the accuracy is 80–85%. We have to be try to be better than that. So this is one reason. The second reason is that now we have 1.7 billion stars to process. So the data set is huge, and we have to find a different way.
And did I understand that your analysis, you know, when you were training the model, it took minutes on the AC922? Was that for your whole data set or just for what you were
No, actually, we have a subset.
Okay, you were working on a subset.
The
Okay.
first subset was 6,000 stars, and the second subset was 300,000 stars.
Right, and your goal is almost 2
2 billion.
2 billion or million?
Billion.
Okay, all right.
Yeah.
What is the calculation? So that's the reason to go to DDL, is to try and reduce your time so much that when you use the whole 2 billion,
Yeah.
it doesn't take weeks, months, years to complete still.
Or centuries, yeah.
2 billion. It's a big number. Here's the next question.
It's just a follow on, because your data set for your learning, you said you had like 6,000 and then a bigger set. Is that learning set from prior classification that was already done, like from the 1996 data, or this is from the new Gaia information?
This is directly from the satellite, and this is part of the data that was released in 2018, 1 year ago, April.
Yeah, so you'd have to be using the same data. That makes sense. And then, but the classification that was already done was prior to that. I mean, I'm just
The one that was done with Hipparcos was done, and we can reprocess that data, but the point is not to reprocess what we already have. The point is to classify all the stars that Gaia got a picture about.
right.
So it's to go further compared to what we already have. It's to complete already what
Right,
we already have.
and I guess I'm asking how do you know what the classification is in your training data, right?
Well, we know what type of stars it is to train the model. When you train the model, you have to say, hey, when you feed the model, you say this star is that type. So you train the model, and then with your training set, you know also what the data is, what your input data is. So then you are able to do the comparison with the prediction.
Right, I'm wondering where the classification is. Okay.
Next thing it seems like you need to train the model to do is to write your books. Because
I will defer this to you.
my mother was an English teacher. She taught me I can't teach anything to read or write, so that's what I learned from her. Any other questions?
At the end.
Oh, here we go.
From the model you took, you mentioned accuracy against a prediction of 94 or 93%. How representative do you believe your training data is to the set of stars that was photographed?
Good point. We don't know. What we know is that we have to carefully select the training data set and the test data set. We have to make sure that the test data set is representative of what we have. Because if we have only one type of stars in the test data set, so we end up nowhere. So we have to make sure that we have enough classes in that test data set. But at the end, on the overall, the full data set, we will see. Maybe there are some, let's say, unknown stars or unknown class. Maybe the European Space Agency will discover something there. It belongs to the astronomers.
Any other questions? Excellent. Then I think we say thank you very much with a round of applause. Thank you.
Thank you to you.